morning. So if you just send hi to me in chat, I will take that as attendance later. Okay. So we'll get started. Let me share my PowerPoint slides to you guys. So if you just join us, just send text to me in the chat, say hi or good morning, whatever. I'll take that as attendance. Okay. Otherwise, let's get started here. So let me close this guy. All right. Let me put this in full screen mode here. Okay, so we'll be still looking at chapter 23, electromagnetic induction for today. And so last time we talked about the if you have a magnetic that is approaching a coil, then there will be induced current in that circuit. Or if you have a setup like this on the right here, where you have a primary circuit and there's a secondary circuit. So if there's change in current in the primary circuit, then there will be current in the secondary circuit being induced. Okay. So in both cases, what you have is change in magnetic flux, which is defined as the magnetic field B times the area of the coil, or through a particular area, times the cosine of theta, where theta is defined as the angle between the magnetic field and the normal direction of the plane of either loop or just a area if you are just looking at magnetic flux. Okay, so then if there's any change in magnetic flux, then there will be induced EMF. Okay, so there will be induced voltage in the loop, and then the induced voltage is responsible for the current. Okay, so put that into equation. If we call epsilon to be the induced EMF, then the induced EMF can be calculated by using this equation: epsilon equals to minus m, where n indicates the number of turns of loops or coils you have, change in flux theta phi over change in time t. Okay, and that means you are doing final flux minus initial flux divided by final time t minus initial time t. And then with a negative sign, that actually is it's coming from the Lenz's law, which says the induced current always flows in a direction that opposes the change that causes it. Okay, so the minus sign comes from the factor that this induced current will oppose the change that causes it. Okay, so there are a couple examples here we went through last time. We'll not going through them again, but you can use them to practice this Lenz's law. Okay. And then we talk about eddy current, which basically is the same thing here. It's about the induced EMF or induced current. So imagine if you have a piece of metal that is moving in the magnetic field, so then you'll have eddy current generated. Okay, this is due to induced EMF. So think about if you have a area like this circular area, then you can think about the change in the flux. So then that's responsible to the change of the current here, or responsible to the induced current here. All right, so if the block is going down, then there will be a force, magnetic force on the current, which will be opposed to that. Okay, so it should be in the opposite direction. Okay, so this phenomenon is also called magnetic damping. Okay, and then we check a few examples on the eddy current in the last lecture. Okay. All right. So today we'll be looking at a new section, checking on a new section here on motional EMF. So look at the figure here on the right. If we look at the top one here, so imagine you have a resistor on the left here, R, and then there's two metal rails on the top here, and then the other one on the bottom here. Okay, so if this setup is being placed in the presence of external magnetic field B here, where you see the cross here or the axis here. So that indicate the B field, the magnetic field is pointing into it's going into the screen, okay, because we are seeing the tail of the arrow, so the arrow goes away from us. So the magnetic field B is pointing into the screen. Now, if you have a metal rod that's movable, okay, but this rod is in contact with the two rails here. Now, if you can make this rod move towards the right, okay, so actually it doesn't matter, it can be moving towards the left, okay, but we'll just give the example of this rod is going to the right, okay. So it has a velocity that equals to delta x over delta t, okay, the average of velocity. So in this case, you can see initially this rod might be in this dashed line here, all right. So then it's moving towards the right. So after delta t time, it has moved by this much, okay, delta x. All right, now you can see initially the circuit, there's a loop as the circuit, so it goes from the two rails up and down, or top and bottom here, and then this rod originally at this position, and then this resistor. So this whole thing here consists of closed loop of circuit, okay? So then you can calculate the magnetic flux in this area by this loop initially, okay? Now final at the time delta t later, then so the B field is not changing if we are assuming it's constant B field, then but the area of the circuit actually has been changed, okay, by this small rectangular here, okay, because delta x that refers to the movement of the rod, and then this L, the length is the distance between the two rails. Okay, so this rectangle area is the change, the increase in the area of the circuit. Okay, so let's say increase of area delta A equals to L times delta X. Okay, so then you can see for the magnetic flux is defined as B times A times cosine theta. In this configuration, the theta should be equal to 0. So it will be just B times A. B is not changing. In this case, A is changing. So that's delta A, okay? So then the overall magnetic flux, that phi should be changing in this case. So if there's change in magnetic flux, then there will be induced current in the circuit, okay? Now in this case, you can apply Lenz's law. It will tell you that this current is going to be in this direction, okay? On the top rail here, on the top rail here, it's going to be to the left. Or if you look at the whole circuit, then it's going to be counterclockwise direction, all right? If this law will be moving towards the left, then this current will be in the circuit will be in the clockwise direction, okay? You can practice Lenz's law here. So, or in the figure shows here, okay, so you can see if this is the, so right hand rule 2 here, it's shown by this right hand rule 2 here, okay, so because you have magnetic field originally pointing into the screen, all right, now you have area increase, that means the flux will be increasing, so then your induced magnetic field should be out of the screen, okay, to oppose that increase in phi, okay? So then here you can see the induced magnetic flux should be pointing out of the ball here. Now, right hand rule 2 will tell you then if you curve your four fingers in the direction of the induced magnetic field, then the thumb is in the direction of the current, okay? So then the current will be towards the left in this case. All right. Now, if that's the case, so then there will be current in the two rails. through the resistor, there should be also current going through this metal rod, okay? So for the metal rod, because there will be induced current over here, now you have the rod carrying the current. It's in the presence of this external field B, original external field B, okay? So then you can apply right-hand rule number 1 to determine what will be the direction of the force, okay? The magnetic force on this rod, okay? So you are going to align your thumb in the direction of the rod, okay? So the figure, I think it doesn't show the right-hand rule one here. The figure doesn't show the correct orientation of the force, but it should be if you have your thumb in the upward direction, because in the rod, the current is going upward, okay? And then your 4 fingers are in the direction of the magnetic field going into the screen. So then the force should be towards the left on the rod, okay? Because the rod is moving to the right, okay? Now any effect, okay, by the induced current, so the overall effect in terms of force on the rod will be the magnetic force on the rod, okay? Should be opposed to that motion, okay? So the motion is to the right, then the force should be to the left, okay? The induced magnetic force should be to the left, okay? So that's what we have here. All right. So, so that tells you what will be the force of that one. Now let's take a look at what will be the induced EMF. Okay, also it lists here that should be equal to BL times V, but we'll take a look on the derivation of this formula. Okay, so we will take a look at this geometry of over here, on this diagram over here. Okay, so as I said, the magnetic force should be towards the left. Okay, so to keep this rod moving towards the right, then you should have a external force F external there. So these two should cancel out, so then you have constant velocity V. Okay, so let's take a look. This is the amount of delta A. Okay, delta A will be equal to V delta T. All right. Now the B field is not changing, so change in flux should be B times V times delta T. Okay. And so this is change in flux equal to B times delta A. So that should be equal to B times V or times L times delta T. Sorry, I was missing an L, but it should be B times delta A. Okay, delta A should be equal to V delta T, which gives you delta X times L. Okay, so this is delta phi. Now, if you do delta phi divided by delta T, times the number of turns of coil M here equals to 1. If you just have one loop here, then the strength of the induced EMF is determined. Okay, so it should be equal to 1 multiplied by delta phi, which is in this expression, and then divided by delta T. So you can see delta T and delta T cancels out. Okay, so then induced EMF, the magnitude will be equal to PVL. Okay, so that's the equation listed a couple of slides ago. Induced EMF should be equal to PVL. Okay. All right. So at any moment, if you have the velocity of the rod to be V, then you can calculate at any moment what's the induced EMF. Okay. Now this is the voltage. Okay. If you do voltage divide by, so this is the voltage across the rod. Okay, on the top end and the bottom end. So if you have this voltage divided by the total length, okay, then you can figure out what's the electric field being produced in the rod. Okay, so BVL divided by L will give you electric field, so which is the bottom equation listed here. So then E is equal to BV, okay, because you divide BVL by L, so L goes away, so it's just B times V remaining. Okay, so this is the electric field caused by the motion in the rod. Okay. All right. Now, let's take a look here. So for the force on the rod, okay, because so if the rod, this is the rod carrying current, okay, now this is downwards because in this figure the magnetic field is coming out of the screen, okay, it's in the reverse direction as the original figure shows, so that's why the current reverse direction here, okay. just in case you are wondering. So the rod is carrying a current, so then the magnetic force on the rod should be equal to I times L times B, okay? Because that's the formula to calculate the magnetic force on a rod carrying current I, okay? So I L B. Now I in the rod should be equal to epsilon, okay, across the rod divided by the resistance in the circuit, okay? So R is the resistance. This is the induced EMF we just checked in the previous slides, okay? BVL is the epsilon, the voltage divided by R, so that's I. So then at the end, the magnetic force on the rod is going to be equal to B squared, because there are two B's, there are two L's, there's one small v, so B squared, small v, L squared. Small v stands for the velocity. And then divide by R, okay? So this will be the magnetic force on the rod. Now to keep the rod to move with a constant velocity v, then the external force here exerted should be having the same magnitude and in the opposite direction, okay? So this force should also have that magnitude, okay? All right. So if we are looking at the mechanical power by the external force you exert on the rod in order to keep it move with constant velocity v, so recall that this is the equation we use, the P, the power, the mechanical power we use in physics 1 to calculate. So power is equal to the force, the driving force. In this case, it will be your pulling force times the speed, okay? That gives you the power, mechanical power. So then this is the F from the previous slides, B squared V L squared over R times V. So then this is what you have for the mechanical power. So B squared V squared L squared over R, okay? Now, in the circuit formed by the resistor, the two rails, and the rod, you can see the electrical power on the circuit, okay, should be equal to, you can use I squared times R, because you know I, okay? I is epsilon, which is equal to BVL divided by R according to Ohm's law, okay? So, the voltage divided by the resistance should give you current. So you have this one squared times R, all right? So then you pretty much squared everything on the top in the numerator. So you have B squared, V squared, L squared. On the denominator, you should have R squared, but you multiply a whole thing by R. So then R squared becomes R in the denominator. Okay, so this is what you have remaining. So you can see the electrical power consumed by the circuit is going to be also equal to B squared, V squared, L squared divided by R. Okay, so looking at these two expressions, it's obviously that the mechanical power you exert on the rod by pulling the rod towards the right, okay, that should be becoming the electrical power consumed by the circuit, okay, because these two are equal to each other, all right? So then you can relate the two energies, the mechanical energy to the electrical energy here, all right? So you are inputting this mechanical energy, and then it turns out as output of electrical energy, okay? Now in this case, we are assuming that the rod and the two rails are ideal conductor. They don't have any resistance. In reality, you don't have this conversion like 100%, okay? But this is in theory, that's what you have, all right? So in this case, you can have a device, okay? So you can construct a device that can convert mechanical energy into electrical energy, okay? So this is exactly what's the mechanism of an electric generator, okay? So for electric generator, you can take in energy in other forms, but you'll convert the energy into mechanical energy to drive the turbines. So then the turbine will have mechanical energy that will be through a device called the electric generator that will convert the mechanical energy into electrical energy, okay? All right, but let's take a look on this example here first. So I will have you guys take a couple minutes to work on this one, and then we can take a look on the solution together, okay? So this one says, as the figure shows here, now the B field is pointing towards you. The rod is moving towards the right, okay? The length of the rod, or the separation of the two rails, is 0.5 meters. this resistor is 10 ohms, right? Now, in this case, it says the uniform B field is 0.750 Teslas. It's asking you to find the speed V at which the bar must be moved to produce a current of 0.175 amps in the resistor. Okay, so in this case, you are given current I. So you have this R as the resistance of the circuit. You can figure out what's the induced EMF. Okay, so I times R will be induced EMF. Then you can use that information because induced EMF will be equal to B times L times V a couple of slides back. And you can solve for your V. Okay, so give it a try. Then we'll look at the solution together. All right, so let's take a look. So for the voltage induced or induced EMF, it's going to be equal to BL times V. Okay, that's one equation here involved. Also, the second equation you want to look at is the I equals to epsilon over R, or the other way around, or you can say epsilon is equal to I times R. Okay, so then in this case, then these two, because this is epsilon, this is epsilon. Okay, so we are taking absolute value of it because then we don't have to worry about the negative sign here, because the direction of the current here doesn't really matter. We'll just look at the magnitude. Okay, from this two equation, we can set it up that BLV is equal to I times R. So then we are looking for V. Okay, we are given this guy, we are given this guy, we are given the I, we are given the R. So we will be solving for V. So V will be I times R divided by B times L. Okay, sorry. in that case, this is 0.175 amps times the 10.0 ohms divided by the magnetic field, 0.750 Tesla times the length of the rod. So I should write capital L because it's given as capital L, okay? But it's the length of the rod, okay? So capital L here. The original formula we derived, we were using small l, but this one tells you you want to use capital L, but that doesn't matter. It's just a symbol, okay? So combine this, or you put all these numbers into your calculator, it should tell you the speed that required to generate 0.175 amps on this device should be 4.67 meters per second. Okay, so that's the speed needed here. All right. Any questions you guys might have? All right. If not, then we'll move on. Okay. So as I said in the previous section, we just check if you have a motion, or if you input mechanical energy into the configuration we saw earlier, you will be able to convert the mechanical energy into the electric energy. So this is exactly what an electric generator does. So an electric generator, the core of it is having a certain coil. Okay, it could be having like this rectangular shape. Okay, most of the time you will have rectangular shape coils. Now in here, although it shows like it looks like a single loop here, but it typically has multiple loops. They being ramped together. So then this is like say n numbers. Typically could be hundreds or even more than that. Okay. Now this loop will be placed in a magnetic field provided by this magnets. Okay, the north pole being on one side and then the south pole being on the other side. So then what you need is you will have input of mechanical energies. Like say you can empower this guy by just using hand. Okay, you can have a device like this. We actually have a pretty good demonstration device in the lab, but we are not going to show it because we are now virtual online now. So, but this is what you have. You are going to crank up, okay, the loops here. So then in this case, you can see B is not changing. All right, in a device like this, the B field will not be changing. The area of the loop would not be changing. All right, but there's other quantity. Remember when we say for magnetic flux is equal to B times A times cosine phi. Okay, so a cosine theta. So phi magnetic flux is B times A times cosine theta. Okay. So let me see. Let me bring this up here. In case you want to view this video later, you can see what I show on my paper here. So the magnetic flux is equal to B times A times cosine phi. So B is fixed in this figure here. A is also fixed here, right? Because the area of the coil wouldn't change. The magnetic field is not changing, but this guy is actually changing. All right, the angle, if you are turning this coil, okay, like this, then this guy is changing all the time. The phi, the angle between the magnetic field and the normal direction of the loop is changing all the time, okay? So then you will have changing of this, okay? So this changes, all right? So then this one is changing. The phi is changing, okay? So then you have delta phi, okay? So once you have delta phi, then it will lead to induced EMF, okay? So then you will have EMF looking back in the figure here on the top here. If you are connecting one terminal of the circuit from this brush over here, carbon brush here, and then the other one on the top here. So then you can have a circuit forming here. Okay, so you'll see if you put a ammeter or galvanometer here, you'll see current being induced in this circuit. Okay, because of that changing angle leads to the changing in flux. Okay, so that's typically an electric generator will how that work. Okay, how the electric generator works. All right. So so again, as I said, because the magnetic flux is changing, and it's because the phi is changing. Okay, so then this is what you have. So assuming we are starting from when the when this is, or let's just assuming this is what you have here. So flux is VA cosine theta here. All right, then you are doing change in flux over change in T. If you imagine you are doing theta phi, if you are doing theta phi over theta T, okay? So then this is what you have, okay? So your epsilon is going to be equal to n, if you look at the absolute value, so n times theta phi, all right, over theta T, okay? Now, to divide this epsilon, okay, you will take theta T approaching the limit of not infinity but 0. Okay, sorry. So approaching 0, that means you'll be doing derivative of theta phi with respect to T. Okay, but you guys don't have to know that. I'm just going to show you the result. Okay, so then the result will be equal to the epsilon. The magnitude of it, it's going to be equal to the equation shown here in the PowerPoint. So epsilon is equal to n times theta times b times a times omega, or the this is omega here. So sine of omega t. Okay, when you do derivative of cosine function, it gives you sine function. Okay, so then this is the expression you would have for the induced EMF, okay, or the voltage provided by the electric field, okay, or by the electric generator. So number of turns of coils times the magnetic strength times the area of each of the coil times omega here, which is the angular frequency, okay, it's the frequency that is being given to the electric generator, okay, so that means how many turns you could have in 1 second, okay, that refers to frequency, or how many revolutions the coil can turn in 1 second is the frequency f, okay. Omega is equal to 2 pi times f, so that refers to angular frequency, okay. So in this case, you can see this will be a sine function, okay. So this, the epsilon will be a sine function like that. Now the sine function, it should have a maximum value, okay, in this case, which will be the magnitude before the sine function, okay. So you can see for induced EMF by electric generator, the maximum you would have is MBA omega. Okay, so this is the maximum value. Now remember, earlier when we are in electricity, we briefly talked about the AC circuit. When we say for AC circuit, the maximum, there's a relationship between the maximum value and the root mean square value. Okay, so root mean square of the voltage is equal to 1 divided by square root 2 of the maximum. So in the US, the household voltage of electricity is 120 volts. That refers to the root mean square. So then the maximum voltage could be higher than that. It should be 120 multiplied by square root of 2. Okay, which gives you roughly about 170 volts. Okay. All right. Now, in a different textbook, you may be seeing the epsilon in terms of, it will be expressed in terms of cosine function, but keep in mind, that's just because sine function and cosine function, they are basically the same, but with a phase shift, okay? So some people prefer to use cosine, but that's up to the author's preference, okay? So don't be surprised if you see somewhere else the epsilon is expressed as in terms of cosine, okay? But just keep in mind they are the same fundamentally. All right. Now let's take a look on the second example of the day on electricity generator here. So this one is on electricity generator. So this one says if you have rectangular coil 25 centimeter by 45 centimeter, has 150 turns. Okay, so capital N is 150. The area can be calculated by this. Okay, 25 multiplied by 45. But these are in centimeters, so you want to convert that into meters. All right. So the coil produces a maximum, so it tells you the maximum EMF, 75. So that means N times B times A times omega is equal to 75, all right? Now it says this is the angular speed of 190 radians per second, okay? So this refers to the omega, okay? So sometimes it tells you angular frequency, and then sometimes it was the wording becomes angular speed, okay? So that's the same thing. That means angular frequency, okay, omega. Because remember, omega is the the quantity we use in circular motion, which is the angular speed, okay? That's the same thing. All right, so it tells you omega is asking you what will be the B field. Okay. So I think this one is quite straightforward. So let's just look at this this solution together here. Okay. So we are given so let me draw a line here. We are given that epsilon maximum. All right. Now epsilon maximum, the peak, the maximum EMF, that's 75, but it can be expressed as an equation as MBA omega, because epsilon is equal to MBA omega sine of omega t. Okay, when sine has maximum 1, then this one has maximum value. Okay, that becomes max. All right, so this is what it has. So this is 75. So basically, we are given 75 equals to n is equal to 150 turns multiplied by the b we're looking for. That the area we can calculate 25 multiplied by 45 times 10 to the minus 4, okay, becomes meter square, and multiplied by 190 radians per second, okay. Keep in mind, radian per second should be what you are using because that's the SI unit. All right, so then you are looking for B. So you do everything on, so you do 75 divided by 150 multiplied by this 25 multiplied by 45 times 10 to the minus 4, and then 190 at the bottom. Okay, all this at the bottom. That equals to your B field. I didn't calculate that for some reason. I don't find it anywhere. But you can calculate this, okay? So that would be your B field, okay? So you're going to do that by yourself. Yeah, for some reason I forgot to plug in the numbers in my calculator, so I don't have it, okay? But you guys can do this by yourself very easily. All right. So this is our electric generator. Any questions you guys might have? Okay, so if not, then we will move on. Okay, so now you guys probably play some electric toys when you were kids. Okay, my sons, they like to play some of them at home. But basically, for electric toys, say for a car, electric car, toy car, of course. So it basically has a motor inside it. Okay, so the motor then actually draws in the energy from electric inputs, say batteries. Okay, so this is what's an electric motor look like. Okay. So it will have electrical input, say motors or say batteries. Then the energy is being supplied into the circuit here. So then this is going to be AC, okay, and AC input, okay. So although you see like you are using batteries are DC power source, but in the car itself, it lets a device convert AC into convert a DC input into AC input. Okay, so then this is what you have there. When this electricity is sent to this guy, so then it's AC electricity, so that means the current will be changing all the time. Okay, so if the current is changing over here, all right, so then there's a changing force on this, okay, on this metal coil. So earlier in this chapter we talked about if you have currents into the coil, then there's a torque, okay, or there's force, magnetic force on the two sides of the coil, and then that produce the torque. Okay, so then there will be torque over here. So then it will be turning. Okay, so then it becomes mechanical energy becomes the output. Okay, so the input is the electrical energy, the output is mechanical energy. So this is the reverse way of an electric generator. Okay, so electric motor is exactly opposite of the generator. Okay, so this just tell you how that works. All right. Now the next section in this textbook talks about back EMF. Okay, so that basically tells you about if you have electric motor. Okay, so when you have AC signal comes in the coil here, let's here changing in the or the movement of the coil here. Okay, so then the mechanical energy is as output, but we just say we just check it. We just discussed this earlier. When there's electric generator, this is exactly what you have. So if the coil is moving in a magnetic field, then there will be induced EMF, which is the working principle for the electric generator, right? So in this case, then as you takes in the electrical input, this guy is moving, but then there will be induced EMF in the coil. That should be in the opposite direction of the input. Okay, so say if you are supplying 120 as the input electric signal into the motor, then because the motor is turning, then there will be back EMF induced. Okay, so this is in the opposite direction of this. Okay, so then it's opposed to this guy. Okay, so the induced EMF here is called back EMF because it is opposite to the original input. Okay, so in that case, then for example, if you are supplying 120 volts, then because of the induced or the back EMF, so then the current going through this guy could be smaller. Could be like, say, this guy could be anything between 0 to the input voltage. Okay, so it could be, say, back EMF could be 100 volts, then the voltage on this guy then should be just 20. Okay, so then you will have less power consumed by this. Okay, the circuit itself. All right. So let's I think that's how much we want to talk about on this topic here. Okay, on the back EMF, just keep in mind when there's an electric motor, there will be back EMF on the circuit. Okay, because of the movement of the coil. All right. So we'll move on to the next section in the circuit and in this chapter here. So this one deals with the transformers. Okay, so in the figure shows here, so for electric power plant, okay, so typically the electricity comes out of the power plant has very high voltage. Okay, so say 12 kilovolts. Okay, then as the electricity being delivered to the consumer, there's long distance delivering. So usually you see high power towers for the, so the voltage here is higher than the one comes from the power plants. Okay, so then in between there's this device called step up transformers. So which it brings the 12 volts to 400 or 12 kilovolts to 400 kilovolts. Okay, so because this guy brings the voltage up, so it's called step up mode transformer. Now, the reason that we need high voltage electricity during the transportation of electricity because If that's the case, then the dissipation of energy during the transformation will be smaller. Okay, so the reason is because the power supplied by the power plant is a fixed number. So power should be equal to voltage times I. All right. So then when voltage is greater, then I will be smaller. Now the energy dissipated during the transportation should be equal to I squared times R, because R is fixed. Okay. So when V is big, I is small. So then this the dissipation of energy during the transportation could be smaller. All right. But now before it just comes to your household, so in this case, a 240 volts household could be a European country here. Typically, they have 240. So then you want to bring this down, okay? So now getting closer to your household, you have a step-down motor, bring it down to say 13 kilovolts, and then there's another one, bring it further down to the household voltage. Okay, now this is still a little bit higher because we still want to keep the dissipation of energy low here. All right. So this is what this figure tells you. So basically, there are two types of transformers. One called step up transformer, one called step down. Okay. Now a transformer, if you look in detail, this is the core part of a transformer, which there are two circuits here. One is called primary circuit, one is called secondary circuit, okay? Or input and output in that way. This is what you see the symbol of transformer in a circuit, okay? If you see this symbol, that means there's a transformer in the circuit, okay? But basically what you have is, so you can supply a electric power into the primary over here, all right? So there's some numbers of terms or coil here, and then there's a different number of turn coils in the secondary, all right? Now, because these are metal sheets over here, okay, so then the magnetic field, because the nature of metal, it's a paramagnetic material, so it will contain the magnetic field inside it, okay? So then magnetic field here and here and here, they will be the same, okay? But you have different terms or coils here, all right? So then if we look at the flux over here, so this should be M times the B field times A, which is phi, the flux, okay? So we can just say phi, because the B and A will be the same, B is the same here and here, the area is the same here and here, so phi will be the same. Now any changing in phi should be also the same, so delta phi over delta T should be the same, okay? So the only thing difference is the turns of coils in the primary and the secondary, they are different. Depends on if you have a step-up motor, step-up transformer or step-down transformer. For a step-up transformer, you have less turns over here, you have more turns over here, okay? So then if you have a voltage Vp comes in, it gets out as Vs, okay? So looking at this, so Vp is equal to minus proportional to the, or Vs is proportional to the number of turns in the secondary, okay, times the change in phi over dt. Now, voltage on the primary should be proportional to the turns of coils in the primary circuit times change of the flux over dt, okay? So in that case, you can see delta phi over delta t the same. So you can look at these two equations, you can derive this equation, okay? So Vs over Vp, secondary circuit voltage over primary circuit voltage should be equal to the number of turns of secondary coils divided by primary coils, okay? So this is the transformer equation. All right, you can use this to determine what the voltage is on the both end, okay, or the ratio of them. And now the power, okay, provided by the power plant should be fixed, okay? So that means the power the transformer on the both sides should be equal to each other. So on the primary side, power should be equal to the secondary side power, all right? But for the primary, it's I times V, PP here, and then secondary is IS, VS, okay? So then this guy will be equal to that guy. So combine this with the transformer equation we had earlier. So then we find the relationship between the currents in the two circuits, okay? The secondary circuit current over the primary circuit current should be equal to the number of turns coils in the primary divided by number of turns of coils in the secondary circuit, okay? Inversely proportional to the turns of coils, because V times I should be equal to, should be the same. So then if V's are proportional to the number of turns of coils, then I should be inversely proportional to the numbers of turns of coils, okay? Excuse me. So then basically, these three equations are all you need for a transformer, okay? All right, let's take a look the examples of a transformer here. So this one says the electric motor in a toy train requires a voltage of 4.5. Now find the ratio of turns of primary coil to the turns of the secondary coils in the transformer that will step the 120 volts down to 4.5, okay? So on this one, we are given that the this is a step down transformer, okay? So that means, so if you draw the transformer, you can look at the symbol of the transformer, okay? Okay, if this is the primary, so then there's a number of turns of coils, there's a number of turns of secondary there. It tells you VP, okay, this is the input. So primary will be the input, it's from the household, okay, 120 volts. Now VS is 4.5 volts, okay. It's asking you what will be the ratio of the primary. So MP, what will be MP over NS? That's the ratio, primary over secondary, okay, turns of coils. So on this one, because we are looking at the number of turns of coils, we are given the primary voltage at 120 and secondary. So then we'll be just using the transformer equation of Vp over Vs is equal to Np over Ns. Okay, so then Np over Ns is equal to Vp over Vs. So simply like 120 divided by 4.5 volts. Okay, that gives you the ratio of the turns of coils in the two. So this would be roughly 26.67 or roughly 27. Okay, so that would be the ratio. All right, of the primary and the secondary. Now, in a problem, you might be given like the currents in the two, then you can calculate what will be the ratios of the turns of coil. Okay, it should be inversely proportional to each other. Okay, but this one is rather simple like that. Any questions you guys might have? Okay, just unmute yourself and let me know. Okay, if you do have questions there. All right. So the next section here talk about electrical safety. So again, I think we touched this little bit in the when we talk about electricity. So in order to have or to prevent any electrical damage or disaster, there will be like circuit breaker, okay, or you can actually have, now that's what we talked earlier, but or you can have like actually the grounding of the appliance, okay. So in case that if there's a broken part of the appliance, then metal is exposed, you can touch the metal by accident. So if the appliance, the case is grounded, then what happens is the electricity, okay, it's going to be, let me see, okay, I think this one tells better, okay, tells what happens better. So what's going to is if the voltage, okay, so if you are grounded, all right, then it will go to go through your body, okay. So then that will cause some harm to your body. But if this is grounded, okay, then you will just go through the ground here. So then go through the ground, okay? So that's what it shows over here. It's safe that it will not go through your body, okay? But it goes through the groundings and then go to the ground, okay? So if this is being proper ground, but if this is not a proper ground, okay? If there's broken ground here, okay? So if this is not grounded, then it will go through your body, okay? And then if it's grounded, then it just go to the ground, okay? Because your body has certain resistance, electric resistance. So the current is kind of lazy. It will not prefer to go through any resistance if there's no resistant path, okay? So it just goes through the ground, okay? So that's another safety measure we can take, okay? All right, I guess we are going to just stop over here for today, and then we'll come back for the there's other sections next time, okay? Any questions you guys have for me at this point? So if not, then that will be it for today's lecture. Okay, I will see you guys on Monday. So wish everyone have a good weekend and be safe and healthy. Okay, bye bye.